Okay, why don't we get started? I'm guessing most of you have looked at least at the notes for the day. You might notice that there's not really a lot of actual words on the pages. It's actually a lot of pictures. My goal today is I want to talk about microscopes. Before we actually talk about cells and all of the things that cells will then combine to become, making tissues, and then making organs, and then making systems, and then making like a person or a tree or something along those lines, I want to spend one more day first just talking about the tools that biologists use. And again, keep in mind, I didn't go to school to be a biology major, so I'm not nearly as experienced in this as I am in chemistry, but biologists really focus on one major tool, the microscope. Right? We need to be able to look at things that are much smaller. Does that make sense? So today's lesson basically is just talking about the history about how microscopes work and how they work. Today I brought out a microscope so I can kind of show you those. Next week, Monday, we're going to do an activity where I actually have you guys use microscopes and look at stuff under microscopes. And yeah, hopefully it'll be fun. I said before, it's going to be different in a lab. I don't really have like a conclusion type purpose to accomplish. Really, my goal on Monday is just to kind of let you play with microscopes. Like honestly, that is kind of my goal. It's just here, look at cool stuff zoomed in really close. One of the things that I'm really excited for is we got Kinsey Ann a really basic microscope, and she's only 3, so she won't use it yet. But like I can imagine her at some point.
I thought you were talking about Kinsey Ann. That was the name of the.
No, Kinsey Ann's my daughter. But one day, like when Kinsey Ann gets to play with like the microscope we bought her, she'll like take a piece of paper and look at it, look at an eraser, right? And I don't know. I think people just find it fascinating just to look at stuff under microscopes. Gabe, you were in my forensics class, right?
Yeah.
Remember the activities we did with microscopes?
That was pretty cool.
Like I would say, you can add to this if you like, but most people want to give you a microscope to play with. You find stuff to look at, right? You grab a piece of your hair and look at that, and then you grab a piece of a eraser and look at that. And, so on Monday, I'm gonna basically have you guys look at a piece of onion. And the reason I want you to look at a piece of onion is because we should hopefully be able to see different parts of cells of this onion. And then after you're done looking at an onion, I'll just give you a bunch of other random things to look at. You can just kind of explore and see what things look like on a microscopic level. Does that make sense? Okay, so let's talk through some of the notes I have today. And while I do that, I'm also going to talk about this handout I found. I took this out of a different textbook. So at some point I'll refer to this, so have it nearby. So, introductory slide here. If the cell is the basic unit of living things, we need to be able to see it. And unfortunately, most cells we cannot see. There are actually a few unicellular, that means like one cell organisms that are big enough for you to see, but for the most part, if you want to see a cell, you need to be able to zoom in with a microscope. Okay. The main type of microscope we're going to work with is the light microscope. But there is actually a second type of microscope called the electron microscope. So, here's just a picture I found of various different types. We're mostly going to work with a microscope like this, where there's only one eyepiece for you to look in. So you have to close one eye in order to see it properly. But, I mean, if you have better and fancier microscopes, some of them might have, like, say, 2 lenses, and they'll converge together so you can keep both eyes open.
Do you have any of those Kinsey Ann?
Kinsey Ann's my daughter.
I know.
Okay, so here's a basic light microscope. Just like this one right here. I'll hold this one up and then we can talk about some basics of it. So, first rule of microscopes, don't drop it. Hey.
She's in a fight.
Oh, you're not going on the trip? Oh, I'm sorry, I didn't know that. Sorry. Here's a basic light microscope. Okay. This particular one is going to have a plug-in, so you'll need to plug this one in for it to work. One of the key components, does it come out? It does too. Okay, maybe it doesn't come out. Is this piece right here? This is the light source. Okay. A microscope will not work unless you put a light source directly underneath it. Okay. The idea being that light should be able to shine through the actual object you're looking at. Okay. So if you don't actually have a light source underneath it, it's no good. Most microscopes will have some sort of dial down here on the bottom. This one's just a turn switch. Some will have like a, I don't know, like a circular disc that you can move. And that disc will either let more light come in or less light. So sometimes you just want to adjust the amount of light that makes it through the sample. Okay. So that's the light bulb underneath. Then this right here, the square, is known as the stage. And usually what we do is we put some sort of glass slip on the stage and we clip it down. Now this particular microscope has like just a little twisty thing right here. And what it'll do is it'll just help keep a little stage slip just in place. Because we don't want it moving everywhere. Does that make sense? So usually there'll be some sort of clips there. The other major parts are these things right here that rotate. Okay. These things are called objective lenses. And basically what you can do is rotate from low to medium to high. I even got a few microscopes that have like an ultra high power. This one right here, where is it here? The red one. The red one right here, you guys can't see this I guess, but it has a 4 on it. Basically it zooms things in 4 times bigger. Then this one in yellow zooms things in 10 times bigger. This one in blue zooms things in 40 times bigger. And if you've got an awesome microscope, you might even have a lens on it that makes things 100 times bigger. Okay. So that's only half of the microscope. The objectives do one type of magnification, but this thing right here does another type of magnification. And this thing is called an ocular lens. Okay. So I have those labeled on this picture here. And most microscopes have an ocular lens that zoom things at 10 times. Okay. Listen for a second. So the way this works, at least for our microscopes, is that if the ocular lens can zoom things 10 times, and then the objective lens can do something like, say, 4 times, collectively, you multiply those numbers. So if you're using the 10 with the 4, it's 40 times zoom. If you use 10 with 10, 100 times zoom. 10 with 40, 400 times zoom. Or the best microscope I have in this lab is would be a 10 by a 100. I did too many zeros. So 10 times 100 means that we could get up to about 1,000 times zoom. Okay. Wow. Now, at least that's for in our school. Better microscopes, as you can see, might even be able to get up into like 1,250 or 1,500 times zoom. So that's going to make things quite small. You can be able to see very small details. 2 more things I want to talk about on these microscopes here. In order to make the microscope focus, what you need to do is once you've got your lenses in place, you need to use one of these 2 different adjustment things here. They're either known as the coarse adjustment knob, that's the larger one, and then the smaller one is the fine adjustment knob. And what these things do, if you can see what's happening as I move this, is it's causing, either it causes the stage to go up and down, or this one here is just causing the actual arm of the microscope to go up and down. And we need to do that so that it comes into better focus. Does that make sense? Like you might see it, but it might be really blurry. So usually use the coarse adjustment knob at first to kind of get things in the right place. And then for like the little details, then you use the little bitty one. I mean, I'm changing this little bitty one right here. I don't think you can even see the thing moving all that much. Because it's just moving just fractions of a millimeter. You guys ever worked with these before?
Yeah.
Some yeses, some nos. Like in the school here, like in science class? Or somewhere else? You haven't used them before? Okay. If you take my forensics class next semester, by the way, you should, it's fun. We'll use microscopes. It was fun, right, Gabe?
Yeah.
Okay. Way to sell it. Okay. One thing I need for you guys to be able to do then is I need you to be able to label a microscope and know all of the different parts of a microscope. Now, I don't know whether you want to put all of these on your word list. Remember how yesterday I kind of suggested make a word list? If you want to, you could put all of these words on there individually. Or maybe you could just collectively just say parts of the microscope. But I need you to know all of these different parts. So I feel like I've talked about most of them. The base is the bottom, I guess. You have to have a light source. You can adjust the light source. The term you use is the diaphragm. The diaphragm is what adjusts how much light makes through. Objectives and ocular are the 2 things that add your magnification. I didn't call it this, but basically it revolves in a circle, so it's a revolving nose piece. And this little piece right here is the arm. Anyways, just make sure you know all these words. Any questions on that? Cool. Okay, let's take a break from our notes for a bit and find the handout that I gave you. Does everybody have one? Okay, so if you look at the handout, I pulled this out of a different textbook. It's got just a few basic instructions. I'm not going to read it all for you. You guys can read. But I do want to talk something about called magnification and field of view. Just so that we've done this before we do our activity on Monday. So this particular last paragraph here just describes what I just mentioned. If you want to figure out how much zoom a microscope has, you have to take the power of the ocular and objective lenses and multiply them by each other. In pretty much all cases, take a number and times it by 10. Just depends on which lens you're using. So either 4 by 10, 10 by 10, or 100 by 10. Does that make sense? Okay, that figures out your zoom, like how much magnification it has. But there's another term I want to talk about called field of view, and I think we need to flip to the next page for that one. So flip to the next page here. Okay. When you look through a microscope, it's probably going to look something like this. You're going to have a big circle, and then most of my microscopes have just a little line with like almost like a pointer. And the pointer is just trying to give you an idea of like where the middle of the circle might be. So you can kind of, if you have to move the slide just a little bit one way left or right, that way you can like line your slide up so that whatever the object is that you're looking at here is right in the middle of the pointer. Not every one of my microscopes does, but most will look something like this. Okay. One of the things I'm going to need to ask you to do then is I'm going to ask you, how big is this thing? Like, what is its distance? Is it 1 centimeter? Is it 1 millimeter? Is it 1 micrometer? Okay. I should talk about this one for a second. We don't usually use those units in physics, but they're very common in biology. This little symbol right here, like a fancy U, is the prefix for micro. It's a micrometer. Okay. So this is centimeter, millimeter. A little U in front is a micrometer. Does anybody remember at all what the like times 10 to the power of for micro is? Anybody know? Not 5. It's actually -6. So like a micro is smaller than milli. So if you can imagine a millimeter, like grab a ruler anywhere. I don't have a ruler nearby. Imagine a ruler, and a millimeter is like that small. Well, a micrometer is 1,000 times smaller than a millimeter. Most of the time when we measure things using a microscope, we're going to be measuring them in micrometers. So very, very small. Okay. One of the things I'll have to ask you then is, well, how far across is this? Okay. And so in order to solve this problem, we come up with something called the field of view. What we do is we take our microscope and we put it on the lowest power we can, which usually means we're doing like, say, 40 times zoom, because that's about as small as we can get. And what we do is we take a ruler and we put the ruler underneath the microscope. And when you do that, the ruler, normally when you have a ruler, like the little markings are really close together. But when you put it under a microscope, they're going to be more like here. And what this might be would be, this is like 4.0, and then this would be 4.1, and 4.2, and 4.3. And normally those would be so closely squished together. But under the magnifying glass, or under the microscope, they're a bit more spread out. Does that make sense? And the field of view then means we need to figure out how far it is from here to here based on our ruler. So hypothetically, let's say based on our ruler from here to here, let's say that it is 1.2 centimeters. Okay. Well, this gives us how far across things are because we know that that's the actual distance because we have an actual ruler underneath there. Does that make sense? What then happens is, let's say we flip to the next lens and we zoom in more. Well, what happens when you zoom in more is if you used to have a picture that looked like, say, this, and you zoom in even more, now you're looking at like just this tiny little section right there, so much more zoom that you won't really have a frame of reference anymore. And so we have to figure out like how big that is. The problem is at a certain point we can't put the ruler underneath the microscope anymore because it's too zoomed in to even help. Does that make sense? So there's some calculations in here that kind of talk about how to figure out the field diameter based on low power and high power. So I don't have them on the board here, but see if you can follow along. In example 8.1, it suggests what happens if the low power lens was 10 times. You guys see, 4 times. It says low power 4 times, and the field millimeters was 4.5 millimeters. Okay. Well, 4.5 millimeters is 4,500 micrometers. Okay. Well, then let's say the guy flips to medium power. Medium power is now 10 times bigger. What that means then is that what you're seeing used to be this big, and now it's this big. It's gotten smaller. So as the power goes up, the size of the things you see goes down. Does that make sense at all? Okay. Now, I'm not really a big fan of how they do these calculations because they have a formula there, but I think probably the best thing to work on would be to talk about this line of work they have right here. Normally, it's 4,500 micrometers. But what's going to happen is 45 micrometers used to be done under 4 times zoom. And now it's going to be done under, say, 40 times zoom. What happens if you say times by 4 and divide by 40? What's going to happen to your number? Good. And the reason why it's going to go smaller is because what you used to be able to see is now zoomed in smaller. Well, what was the number there? It ends up being, 450. Which I think makes sense because from 4 to 40 means that like you went 10 times bigger in terms of your zoom. So therefore the actual size of your objects should be 10 times smaller. Does that logic make sense? If you go from 10 times bigger zoom, it means that your objects must now be 10 times smaller as to what you're looking at. So I'll walk you through calculations when we have to do this on Monday. I'm not the biggest fan of how they show it on this particular example, but basically the idea is we got to figure out how big are the things we're looking at. Okay, one more topic here, then I'll go back to my notes. The other thing we need to do is we need to be able to prepare a slide so that we can actually look at it under a microscope. The term we use is called a wet mount. I think the reason why we call it a wet mount is because we need to use water. Water has a lot of really cool properties, but one of them is that it helps kind of adhere the slide and the cover slip and the actual sample all together. Honestly, I think it's just easiest if you just look at the diagrams here. What's going to happen is I'm going to give you a little glass slide, which is, quite small. And what we're going to do is we're going to put a little sample of something on top of it. In our lab, we're going to do an onion. And then what you do is you add just a single drop of water, and you put a little glass slip over top of it. And basically, it should adhere together and give you a sample you can work with. You guys ever done this before, by the way?
Yeah, I've done that.
You've done this before? Everybody else is kind of saying I know? Okay. I mean, if you have or if you haven't, that's not a big deal, because we'll actually do this on Monday. I feel like I'm not really doing it justice by just describing it to you, because I'm telling you in words and it doesn't help. So is it okay if you just kind of pause on this thought until we actually do this? But one of the things you may have to do, though, is in order to make a sample work, you may have to stain a sample. And we're going to do this on Monday. What color are onions?
White.
Yeah, almost to the point of like see-through, actually. Like they're clear. And that causes a real problem because we can't really see the onion cells. So what we do is we add a drop of stain. Now we're not talking like paint stain. We use a chemical called methylene blue. And what it basically does is it highlights all of the key areas in a blue color rather than in a clear color. So the picture that's next to it there basically suggests that if you want to stain something, we still use a little bit of water, but we also add just one drop of the stain. And we do basically the same thing. Put the cover slip over top, but you just have a piece of paper towel to soak up any extra stain, because otherwise it gets everywhere. And it will not only just stain the sample, it will stain your hands and clothes and that stuff too. So Does this make any sort of sense? Yeah. Okay, save this till Monday. Like, I feel like I'm not doing this justice, so I'm just going to point this out to you guys right now. We'll do more of this on Monday. So, back to our regularly scheduled notes. Okay. We work with light microscopes because I can afford light microscopes. There's a second kind of microscope. These are cool, but we can't afford them. They're called electron microscopes. And basically what happens in a light microscope is we shoot light from a light bulb at a sample and we look at it. Well, an electron microscope does something similar, only it shoots electrons at a sample to help you get a picture of what's happening. It's actually really cool because electrons are so small, they're pretty much the smallest unit of matter we know of. In terms of like subatomic particles, you guys know how like we're talking about cells in biology? Well, smaller than cells would be molecules, and smaller than those would be atoms, and smaller than those would be elements. And smaller than elements would be protons, neutrons, and electrons. The way an electron microscope works is it shoots electrons at things. Okay. I want to describe this. How does a blind person find their way around? Yeah, they use a little stick thing, right? And so if I were blind and I wasn't sure where I was going, if I poke something and it hits something, I know there's something there. Does that make sense? Well, it's kind of the same thing with an electron gun. If the electrons hit something, then there's something there. And if the electrons don't hit something, or they go further and then bounce back perhaps the other way, then there isn't something there, or at least it's further away. Does that make sense? Yeah. Basically, electrons get shot at a sample. And depending on how those electrons react, depends on what the picture looks like. So here are some pictures. I'm going to fast forward in the slides of some of the things that you can see with electron microscopes.
How it looks just like that.
Like these are like, I believe this is like bacteria. Like these are like about as small as you can get. Like this might be a mold of some kind.
Yeah, can we look at mold?
I believe this is a flea. This is the surface of a flea. Just look at the detail that you get off of this because of electrons bouncing off of it.
That's what you get from electron microscope.
Electron microscope, yeah.
Side of this here. Look at this stuff for a field trip.
I'll look into it.
Yeah, we should actually do that in Calgary.
I'm not sure they have one in Calgary though. We have to go to the U of A. Do they? Okay.
Yeah, the spark signs.
Cool. I'll look into it. So, I found a picture online. We're not talking a high school lab. High school labs don't have one of these, right? Like these are millions of dollars. No, this is not like a desk microscope. This is like a huge instrument that fires electrons at things. So, here's a picture that I found that tries to describe what happens, but basically you've got a gun and it shoots electrons. And depending on how those electrons pass through different things depends on the picture you get. So. I feel like I can't adequately describe an electron gun, one, because I don't have one, and two, like I said, I'm not a biology major, so I've actually never used one before. So, I mean, I know what they do, but I've never actually tried it. So yeah, I'll look into the science center thing. That could be cool. Here's what I do want you guys to know, though. I want you guys to know the difference between the two microscopes. So you may even want to add electron microscope and light microscope to your word list. It's up to you if you want to add that there. But I need you to know the difference between the two. First, I'd like to just use an analogy to show you how much better an electron microscope is than a light microscope. I found this picture online somewhere. Imagine that you had a rock, and then imagine you had Mount Everest. That would be the comparison between how good a light microscope and an electron microscope would be. A light microscope would be able to see Mount Everest. So, I mean, all I can see is this big, massive mountain. That's how good a light microscope is. An electron microscope could see a rock. 100,000 times smaller. That would be like being in outer space and like someone on the moon looking in and being able to see what you're typing on your smartphone. Right? Like we're talking find a license plate from a satellite kind of technology here. That's how much zoom it has.
I've seen like camera lenses that like the skies like in the mountains, like it looks like it's just like beach and water, so like it zooms in, like sees it.
It just keeps going, right?
Yeah.
It's cool. Okay. So here's some of the facts I want to point out between the two. Light microscopes, you can actually see them in the color that it is in. So like you can see reds and blues and yellows, which is kind of cool. But one of the things you might have noticed about the pictures I had coming up next, I mean, we can get shades of gray, but you guys have heard the term, like, say, monochromatic? Like, basically, you've got a spectrum from white to black. So you get shades of gray, but you don't actually get color if you use an electron microscope. You get a pretty large field of view in a microscope. But, I mean, if an electron microscope zooms in that close, I mean, we are talking the smallest stuff we can find. They're cheap. Well, okay, I shouldn't say cheap. If you bust one of these, it's going to cost you a couple $100. But a couple hundred is better than a couple million. So please don't break the microscopes, by the way. Be very careful with them. Light microscopes, this is really cool. It can view living objects. So we can actually put live specimen under a light microscope and possibly be able to see it. But an electron microscope, it needs to be dead. Like, we're firing electrons at it, so it's probably better if it's not alive. Okay, here's something cool. The magnification is somewhere in like the 1,000 or so range. We can go like, say, 40 times or 100 times or 400 or 1,000 times zoom. Those are our typical zooms. So I think 600 is kind of in the middle of all of that. For the magnification of an electron microscope, 500,000 times, maybe even 1,000,000 times zoom. That's incredible to be able to see that small. Okay. In terms of units, this symbol right here is a micrometer. This symbol right here for N is a nanometer. You guys have maybe heard of like nanotechnology?
Yeah.
Like, that's basically as small as anything can probably function, is the nanometer. In terms of like, I mean, again, I can't even do it justice. I mean, it's so close together that it's, I believe a nano is to the -9. So that's like 0.00000000001. Like, this is the smallest thing you can almost imagine. You okay? Okay. Okay, okay, I skipped a slide here. You should probably add these guys right here to your word list, because they're bolded. Electron microscopes, there are a couple of different varieties. Again, I don't have experience with these, so all I can tell you is what I've learned myself. But there are a couple of different varieties. So I'll just read off what I've got here. You guys still with me? I'm really distracted. Okay. A transmission electron microscope. The idea is that electrons are supposed to go through the substance. And it makes you a 2D image. That's supposed to be the idea. You get a really thin slice, and either the electron passes through or it doesn't. Okay. The scanning electron microscope basically tries to scan the surface and make a 3D image. I think the confocal is kind of similar to the transmission one. What it does is you scan like each layer, one layer at a time, and it makes a whole bunch of 2D images, and then it renders a 3D image by putting a 2D image on top and on top and on top. And eventually it's like a whole bunch of cross sections put together, and it makes like a three-dimensional picture again. And the last one here, apparently a scanning tunneling microscope can zoom in as much as 2 million times. So that we can see DNA itself.
So like the curl.
Yeah, like the double helix spirals. So, anyways, can you guys just add these to your list of things to know about? The 4 different kinds of electron microscopes. They're in your book. Like, there's probably a bit of a blurb on each of them there, but I've given you the Cliff Notes versions here. Does that make sense? Wait, what have I missed? We talked about all of this.
There's one more word.
Ah, there you go. Okay. Last slide, then we'll take a break here. I've already used the first word bolded, staining. Maybe you want to add this to your notes. We're going to use a chemical called methylene blue. It probably spells like it sounds. Methyl is M-E-T-H-Y-L. And then add an "ene" at the end, so E-N-E. It's methylene, and then blue. And that particular chemical, basically the way it works is it dyes the substance. So if you have a clear substance that's really hard to see, what it'll do is it'll coat the outside edges with blue, because it's blue, right? And it'll make it just a little bit easier to see. Sometimes the term we use is contrast. Do I have that on here? I don't. Have you ever heard that word before, using like a contrast ink to try to help make things show up? Medical professions use contrast. Like they put a dye into, say, like your an organ, perhaps. Oh, and the idea being that then it'll show up under an MRI or an X-ray or something along those lines. You guys ever seen that in a medical drama before, where they had a contrast dye to help things show up? Same concept.
Oh, yeah.
Okay.
No, I think so. Like, what are you talking about?
Oh,
yeah. Oh, yeah. No, I honestly, like, I want to flip it, but I think
Paying close attention. Okay. The last technique, I don't have one of these. I have used one of these in chemistry before. It's called a centrifuge. The idea behind a centrifuge, you might have even seen one on, like, say, CSI. You take a vial, and you put the vial into a machine, and it spins around in circles, like wicked fast.
Oh, yeah, actually, that thing.
And the idea behind spinning it in circles is it should separate into layers based on density. And so the most heavy, dense stuff should go to the bottom of the test tube, and lighter, smaller stuff should rise to the top. The idea being that you can separate things into pieces. So you might have white blood cells at the top, but red blood cells at the bottom. And that's the idea here. You want to separate them so that only you see the red blood cells, or only you see the white blood cells. You guys ever heard of this or seen this device before? The like spinning around in circle device?
It's got like two things and you put it in there.
Yeah, and it whips it around. I mean, I imagine kind of like one of those things they use to test astronauts before they go into space, where they work them around in circles to make sure they don't black out. Yeah, like G-force thing, right? Only it's not massive, it's just a small thing. So, I have used a centrifuge before myself in university. Okay, any questions? Again, bios, guys, give me one more minute, okay? I'm almost done. Bio is a different section than chemistry. There's no examples. Like, there's no calculations. Like, at least in chem and physics, I'd be able to give you, like, a worksheet. I struggle with bio, because, I mean, one, it's not my major, but I don't have anything to give you and be like, here, practice this. Because it's not that kind of science. So here's my list of things that I think you could work on if you feel like you need something to do. So I would always recommend read over your textbook. Like, that's probably a worthwhile thing to do in biology, because I can tell you some stuff, but it doesn't hurt to read even more. Okay. There's a few different sections in your book where there's some questions you could look at. Other than your textbook, though, you could also work on, for example, the assignment. I believe has a few questions on microscopes. And if you wanted to, you could even start considering what your research project or your construction project looks like. But at least right now, we're kind of limited. Tomorrow, though, is a very big day. Tomorrow, we're going to talk about all the different parts of a cell. Things like the nucleus, chloroplasts, if it happens to be a plant cell, mitochondria. So tomorrow's going to be a very busy day because we're going to have a lot of terms to write down.
Isn't only a cell wall
in a plant cell? Yeah. Yeah, you guys might know some of this stuff already. Okay, anyways, I'll stop. If you guys want, take a break. Class goes until 2:05, so you have like 40 minutes to do stuff. Yeah. Okay, yeah, give me 1 second. I'll just stop this for a second.